In this next part of 4.4, our objective is to find the average value of a function and use the mean value theorem for integrals. Well, mean value theorem is mean value theorem. Let's go back to when we talked about the mean value theorem first. That was when we were discussing derivatives. What did mean value theorem looks like? Well, the function's continuous, the function's differentiable, and when that happens, the derivative at some value c will equal the average rate of change, f of b minus f of a over b minus a. How does this get us to the mean value theorem for integrals? Well, let's take the integral of both sides of this equation and let's see what we can do with it. Now the b minus a that's in the denominator here, this can be treated as a constant multiple and we can pull this out so that it looks like that instead. Then we can start thinking about what the fundamental theorem of calculus is. The antiderivative is the integral. So if we're taking the antiderivative of the derivative, that leaves us with just the function f of c. Kind of like they are canceling each other out. They are inverse processes of each other, the antiderivative of the derivative. Similarly over here, this is saying the antiderivative of f, but there's no f prime here, so we have to write this other side a different way. Now let's continue to have the 1 over b minus a constant here. The antiderivative of little f we write as big F. So let's write it as big F for both of these. And then let's again think about the fundamental theorem of calculus and say, well, what does capital F of b minus capital F of a also represent? Well, this is the same as saying the integral from a to b, the definite integral from a to b of the function f of x with respect to x. Now, rearranging this a little bit takes us to the mean value theorem for integrals. Leaving it like this actually tells us the average value. The f of c in this case, this is called the average value of the function f of x. This is the average value of the function. Now we're going to look at what this means to us graphically, and I will show you how this takes us to the mean value theorem for integrals. So this part's called the average value, whereas the c that's in here, c is the mean value. The expression right here, 1 over b minus a, we can multiply to the other side so that it looks like this, b minus a times the f of c. So let's write it with the f of c first, and then the b minus a multiplied to it. Not because it matters the order, just because it's how we're going to usually see it in the textbook. And then that's the definite integral from a to b of f of x dx. I just want to look at it this way because graphically to us, this part means the net area between the function and the x-axis. The definite integral means the net area bound between the function and the x-axis. Given a picture, let's say f of x is like this, and let's say a starts here and b starts here, then the definite integral is all of this area in here. Nothing's below the x-axis, so nothing is negative. So we have that shaded region right there, so it's the area of that. That's the definite integral. And this part right here is saying that there is a function value, that's the function value, so that if I were to draw a line at that function value, and again, that function value corresponds to some c value, that could be the height of a rectangle that is the exact area of the shaded region. where the f of c is the height of it, and the width of that is b minus a. So we find the area of a rectangle by saying its height, this is the height, and this is the width. So the mean value theorem for integrals just basically says there is a perfect rectangle out there such that if we found it, the area would be the same as the definite integral, or the exact area of the function between of the region between the function and the x-axis. Let's get our notes a little bit more organized here. So let's take this to exactly what is the mean value theorem for integrals. Now this is the mean value theorem. You saw how it comes from the other mean value theorem, so it's the same mean value theorem. It's just taken into a different context for integrals. If f is continuous on a function a to b, if f is continuous, so again, we're not going to have any area leaking out since we're using area to help us describe this, then there's a number c in the interval. So again, because this is in an interval, this number c, which is called the mean value, this number c is an x value. So this x value can be found such that when I take the integral, the definite integral from a to b of f of x dx, I can find that x value such that the y value corresponding gives us the height of our perfect rectangle. So this part right here is the height. This part right here, yep, there we go, let's fix that, is the width. Therefore, that section right there is the area of some rectangle, which will give us the exact area bound by the function and the x-axis. So the average value is that y value. So the average value, and this should say, so let's correct it a little bit, this should say the average value of f of x. The average value of the function we're talking about is when I have that height by itself. So f of c is the b minus a divided to the other side, 1 over b minus a times the integral from a to b of f of x dx. You can kind of associate this with how do you normally find averages. Well, the averages we find by adding up a bunch of numbers and dividing by how many we have. So the integral part comes from the sum, remember, S for sum. So the integral part is the adding up, and then this is the dividing by how many that we have, in essence. So again, the average value comes from the perfect height of, or the height of our perfect rectangle. We could say it like that, the height of our perfect rectangle. So again, just taking that visual in there, and I'm going to make this a little bit more of a dramatic f of x from a to b. So our area that's in there, that exact area, is this, and that's the definite integral. Whereas mean value theorem for integral tells us that there has to be some point at which I can draw a rectangle that has the exact same area. And I'm going to do that in the matching color of this one so that you can relate them. So C is some value in here such that I can draw and get that area, and that area is the same as the definite integral. So how do we use that? Find the average value. So first of all, you just need to know what is the formula for the average value. I see the average value of f of x, and I know the formula. F of c equals 1 over b minus a times the integral from a to b of f of x dx. Write that down. Then plug the stuff in. Here's the function. Here's the a to b. F of c then equals 1 over 3 minus 1, integral from 1 to 3 of x squared plus 1 dx. We know how to do the definite integral because that's the fundamental theorem of calculus. So let's simplify a little bit. That makes 1/2. This antiderivative is x cubed over 3 plus x. We don't need the minus c because we're going to be subtracting. We plug in the upper limit first, and let's make some room up here. So plugging in the upper limit is 3 cubed over 3 plus 3 minus the lower limit. Let's put some parentheses so we don't get lost. 1 cubed over 3 plus 1. And then we'll do some simplifying. So doing some simplifying, and we get 16 thirds. So there's our average value on that interval, 16 thirds. If we take this a step further, then find all the values of c, so find the x value guaranteed by the mean value theorem for integrals. Well, remember, that's the x value that goes with that y value. So if I just found that f of c equals 16 thirds and I want the c, that basically is saying find the x value such that the y value is 16 thirds. So the function is x squared plus 1, that's the function, x squared plus 1 equal to 16 thirds. We're looking for that x value. C is that x value. Instead of x squared, because there's a c here, it probably makes more sense to write it as c squared plus 1 equals 16 thirds. And then we solve for that value. So subtracting 1, this looks like c squared equals 13 thirds. Take the square root, c equals plus or minus square root of 13 thirds, but on the interval 1 to 3, c is only the positive of that value. So that's the one that they're looking for. Let's look at it in a different context. The velocity of an object is given by this function. Find the average velocity. Well, we found average velocities before given position. This is not given position. This is given a velocity function. So anytime they say find the average of a function you already have, that is saying find the average value of that function. So the average value is our formula, 1 over b minus a times the integral from a to b of f of x dx. That's our average value formula. F of c equals, that's our average value equation. Well, this is not f, this is v, so we will say v of c equals 1 over, this is our a and our b, so pi minus 0, integral from 0 to pi of sine of t dt. Let's evaluate this side, so that gives us 1 over pi. Antiderivative of sine is negative cosine. And put our limits 0 to pi, then plug in upper limit first. So negative cosine of pi minus negative cosine of 0. And we know cosine of pi is -1 and cosine of 0 is 1. So let's see what this simplifies to. The negative 1 is +1 plus 1, so that looks like it's going to be 2 over pi. There's our average velocity. Let's see what's next. At what point or points in time over the given interval does the object reach its average velocity? At what points in time? So they're basically asking us, what is the t value that goes with that v value? So what is the t value when v of t equals 2 over pi? That's all that's asking. We know our velocity function, sine of t equals 2 over pi. Now let's solve for t. This is not a value on our unit circle, therefore we'll have to use a calculator and do the inverse sine of 2 over pi. Type that into your calculator, take it to at least 3 decimal places. And you know what? Better safe than sorry. 0.6901. That's past 3 decimal places, but past is always better than not enough. Yay.